Namaste. Hope you are doing well. Today we will solve the 8th question of ISI MSTAT 2022 PSB. And yes, from the look of it, it seems to be an inference-based question. And it's asking, it's interesting. You have historical data, which is represented by this distribution. Then there is new theory, which is suggesting this distribution. And then there is a setup around it that you have to compute the lambda given, and then there is a test between the historical data and to determine whether historical model is more accurate or the new model is more accurate, and you have to work around the critical region of that test. All in all, a very interesting inference problem. So let's get started. Before connecting the dots, we would have to have a good summary of the information given to us over here. And this does a good job. You note that you have a historical data model and there is a new theory which suggests that the same variable, rather the square root of that variable, is following a certain model. And then there is the stuff about lambda given. So the information in these paragraphs summarized in 1 or 2 lines. So once we have that somewhere written or at the back of our mind, it's easier to proceed. Now to connect the dots. There is information about lambda, but how would you put math into the words? And another thing that needs connection of some dots is, here you have x directly, but here you have root x. So somehow you have to make sense of the expectation of x with expectation of root x to compute lambda. So how do we do that? To put maths into English, quite simple. You have lambda such that the expectation of the variable under the old model has to be the same as the expectation of the variable under the new model. And we also know, to mathify it even further, we also know that by old model, what we mean is this distribution. By the new model, what we mean is this distribution. Okay, we have it, the maths around English. But now, how do we make sense of the expectations of root x with x? We use the formula of variance. Now, variance of any variable being the difference of the square of the variable's expectation and the expectation of that variable, whole square of that. That is a fairly known formula. We just have to think about root x in that, because we have a concrete formula, an established formula, and that should be our first go-to point. And just rearranging, we take this is, by the way, root x whole square is x. Taking this to the LHS and other things to RHS, we have this. So now we have something that is linking root x and x, the expectation of x with appropriate expectations and variances of root x. We'll be using this. Now we can use this information combined with this and compute lambda. Now, what's given over here, that's exactly what is following. And instead of expectation of x, we have, using this thing, the substitution over here. Now, x is a chi-square. When x is a chi-square variable, what's the expectation? The degrees of freedom. You have to remember these things. And in that case, it's 1. And when we talk about the variance of root x, and once again, you have to be comfortable with the idea that even though we have a root x over here, the distribution of root x is itself specified. If it's easier in this way, you can think of it as y rather than root x, because we are accustomed to look at variables and then append symbols like root x or x cube and other things. But notation like this itself is valid. So you have the variance of and a random variable which is exponential distribution with mean lambda, and the variance is going to be square of that. And yeah, so, and the expectation itself is lambda, so the square of that is lambda square. Pretty simple. You have this, and that's it. Lambda is 1 by root 2. Yeah, you may have noticed that lambda equals to minus 1 by root 2 is also potential solution to this, but it's not valid, because if lambda is negative, then this thing doesn't make sense. So lambda has to be positive, and the positive solution is the value of lambda. Okay. Now we have lambda. Now on to the second part of the question. You have to correct some dots here as well. It's talking something about most powerful level test alpha would have this critical region, blah, blah, blah. So in this context, what is the most powerful test? That is the first thing to look at and connect the dots. Now, if you notice, the null hypothesis and the alternate hypothesis are simple. By simple, we mean that the distribution is completely specified, which indeed it is. And because the hypotheses are simple, by the Neyman-Pearson lemma, the likelihood ratio test is going to be the most powerful test. Then comes the question, what do I use? What statistics do I use? And by statistics, I mean the random variables to use. Should I use xi? Should I use root xi? Is there something else to use? And the answer to that is choose root xi. There's a reason for it. Root xi is properly specified in the new version or in the under the alternate. And under the null, even though you don't have a root xi, there's a very important piece of information that you should remember. That if there is a variable following normal 0, 1, then the square of that random variable is going to follow chi square 1. It's a very important thing. It's a very important transformation. And so the other way around, you can check it by the Jacobian method, is when you have a variable having chi square 1, the square root of that is going to follow a folded normal distribution. And by folded, I mean it's on like, if you have a normal distribution like this with the mean, a folded would mean something like this portion being folded to the right side, and it becomes something like this. So it's like you're taking the left side and folding it onto the right side, because it cannot be the data structure that we have, negative values cannot be there. So that's it. And the distributions are also given. This is the distribution under the alternate of the root of x, which is exponential, pretty standard. And this is actually, if you look at it carefully, it's this thing. So this thing multiplied by 2, right? And this thing is completely coinciding with the normal distribution PDF. But because we folded it, as I was explaining earlier, we folded it and got something like this. It means now that the area on the right hand side, that would be amounting to, if we just fold it, that would amount to exactly half. And to scale it, we have to divide by half, so we end up multiplying by 2. And that's why this structure comes and which simplifies to this. So this is the PDF of, you can call it the folded normal distribution. That's what I like to call it. Perhaps that's what its official name is, I don't remember. Now, the likelihood ratio is, we'll start with one statistic only, and then we'll generalize to n number of observations. It's simple. It's the ratio of the PDF under null and alternate. And if you substitute these two values over here, you will get something proportional to this. And I'm not concerned about the constants, because whenever we are constructing tests, we should focus on the statistics only, not the constant. It just becomes easier to save time when you're writing these things in the examination hall. And your marks won't be cut because you are sticking to relevant things only. And once you simplify this, you take this up, you get something like this. And this is the point when, perhaps you can see the future, how this is going to connect to this. But still, let's proceed. So that was the likelihood ratio for one observation. For multiple observations, it's same as multiplying the likelihood ratios for individual observations, because we have independence of observations over here. And then the likelihood ratio is going to be proportional to this. And this thing at the top is exactly what we see being asked in the critical region. So if we take it as t, then we notice that as the value of t increases, this entire value, because it's raised to the negative, is going to decrease. And if your likelihood ratio is going to decrease, it's essentially giving you more information against the null hypothesis. And an intuitive way to understand this is because the likelihood associated with null hypothesis is in the numerator. So a higher value would mean more evidence for null hypothesis. A lower value would mean less evidence for null hypothesis. And because t plays this role, we can say that the test would be such that a higher value of t is going to give us evidence against H0 or rejection of H0. And once we figure this out, that's it. We have the structure of the test logically derived from these steps. And we say that the test is going to reject at level alpha, rejects H0 at level alpha when t is greater than c. And we have to write a concluding line as well, that here c is such that the probability of type 1 error or rejecting the null hypothesis when it is true is alpha. And this is important because the question is also saying that c is a constant that depends on alpha. And we make that link over here that c is a constant that depends on alpha. And indeed the critical region is of this form with the statistic is greater than some value. That's it. And some base to value of base is, if you notice, the problem had many crucial things playing a role in a subtle manner. But one thing that we noticed was the choice to make the statistic under consideration root x. And that did come up with the intuition of linking chi-square with folded normal distribution, because the other way around would have been difficult, right? Taking x over here would have meant taking the distribution of the square of an exponential distribution. And that may not have been very conventional for us to deal with than a folded normal distribution. So identifying the root in the problem helps us to get to the root of the problem quicker. And we make the relevant transformation. In this case, this is the transformation to compute what we want to compute quickly. Hope this was helpful. And if you like this, then the request this time is to think of a test, could be statistical or very deterministic, doesn't matter, which can help you actually decide whether you are still the old you or are you becoming someone who you want to be. You are becoming closer to the person you want to be. Try to think of a test. What would be a good way to assess that? Take care. Hare Krishna.